Alright, looks like we are live. Let me open the table of content first. Okay. On previous session we are on not that one, this one. We are on chapter 13 on section summary here. So let me open that. Alright. Okay, we are on this summary section. Let me read that. We have seen the introduction of a mature operating system, virtual memory. We have seen the introduction of a mature operating system subsystem. It is virtual memory, okay. The virtual memory system, again, VM in here stands for virtual memory in this context. Where is it? This one, right? Virtual memory, not virtual machine, but yeah. Sometimes people call operating system as virtual machine because of the virtualization that operating system do, like for example virtual memory here. Okay. Anyway, the virtual memory system is responsible for providing the illusion of a large, sparse, private address space to its running program. Its virtual address space contains all of a program's instruction and data, which can be referenced by the program via virtual address. Its virtual machine system is responsible for providing the illusion of large, sparse, private address space to its running program, so its program has its own address space. Its process, I guess, has its own address space, and its virtual address space, or usually called address space, contains all of a program's instruction and data, which can be referenced by the program via virtual address. The operating system, with some serious hardware help, will take each of these virtual memory reference and turn them into physical address. Okay. With some serious hardware help, we'll take each of these virtual memory reference and turn them into physical address, which can be present to the physical memory in order to fetch or update the desired information. Okay. Turn them into physical address, which can be present to the physical memory, that is the hardware side, I assume, in order to fetch or update the desired information. The operating system will provide this service for many processes at once, making sure to protect programs from one another, as well as protect the operating system. The entire approach requires a great deal of mechanism that is lots of low-level machinery as well as some critical policies to work. We'll start from the bottom up, describing the critical mechanism first, and thus we proceed. Okay. Alright, let me read this aside first. Okay. Aside, every address you see is virtual. Okay. Ever write a C program that prints out a pointer? The value you see, some large number, often printed in hexadecimal, is a virtual address. Ever wonder where the code of your program is found? You can print it out too. Oh, and yes, if you can print it, it also is a virtual address. Okay, where the code of your program is found? Interesting. In fact, any address you see as a programmer of a user-level program is a virtual address. It's only the operating system, through its tricky technique of virtualizing memory, that knows where in the physical memory of the machine this instruction and data values lie. Okay. In fact, any address you can see as a programmer of a user-level program is a virtual address. Any address, okay, that we see as programmer of a user-level program is virtual address. Okay. It's only the operating system, through its tricky technique of virtualizing memory, that knows where in the physical memory of the machine this instruction and data values lie. So never forget, if you print out an address in a program, it's a virtual one, an illusion of how things are laid out in memory. Only the operating system and the hardware knows the real truth. Here's a little program, va.c, that prints out the location of the main routine. Oh, okay. Where code live. Okay. I mean, we're printing out the function address, I guess. Right? But I'm curious. Is the location of main function consider the entire program location too, like the start of the program memory address? I'm not really sure. Okay, the value of a heap allocated value returned from malloc, and the location of an integer on the stack. Printf location of code, okay. Malloc, the value of heap allocate value. Return from malloc, okay, and the location of an integer on the stack, right? This one. When written on a 64-bit Mac, we get the following output. Okay. Yeah, this is the virtual address, I guess. From this you can see that code comes first in the address space, then the heap, and the stack is all the way at the other end of this large virtual space. All of these addresses are virtual and will be translated by the operating system and hardware in order to fetch values from their true physical location. All of these addresses are virtual and will be translated by the operating system and hardware in order to fetch values from their true physical location. Okay. I mean 186. Is this the size for malloc? Okay. And yeah, we didn't free the memory from malloc, and we are returning non-zero value for main function here. Just something to keep in mind, I guess. The nucleus of a multi-programming system. The first paper to suggest that the operating system or kernel should be a minimal and flexible substrate for building customized operating system. This theme is revisited throughout operating system research history. Introduction and overview of the Multics system. Okay. A great early Multics paper. Here is the great quote about time sharing. The impetus for time sharing first arose from professional programmers because of their constant frustration in debugging program at batch processing installation. Okay. Thus, the original goal was to time-share computers to allow simultaneously access by several persons while giving to each of them the illusion of having the whole machine at his disposal. Is this the concept of cloud computing? I mean, it seems like something the cloud computing do nowadays, right? Like sharing the computers by several persons while giving to each of them the illusion of having the whole machine at his disposal, right? So there's one computer but several person using the same computer. Maybe something like that. Programming semantics for multi-program computation. Okay, programming semantics for multi-program computation. An early paper, but not the first, on multi-programming. Okay. Main computer symbiosis. A funky paper about how computers and people are going to enter into a symbiotic age. Clearly well ahead of its time, but a fascinating read nonetheless. Are going to enter a symbiotic age. How computer and people are going to enter a symbiotic age. Clearly well ahead of its time, but a fascinating read nonetheless. Okay. Time-sharing computer system. Probably McCarthy's earliest recorded paper on time sharing. In another paper, he claims to have been thinking of the idea since 1957. McCarthy left the system area and went on to become a giant in artificial intelligence at Stanford. Oh, artificial intelligence at Stanford, okay. Including the creation of the Lisp programming language. See McCarthy's homepage for more info. Okay. Oh, wait a minute. Why is it www test forma? Interesting. It is usually www.forma, right? A time-sharing debugging system for a small computer. A great early example of a system that swapped program memory to the DRAM when the program wasn't running, and then back into core memory when it was about to be run. Okay, reminisce on the history of time sharing. Okay, a terrific historical note on where the idea of time sharing may have come from, including some thoughts toward those who cite Strachey's work as the pioneering work in this area. Okay. For crying a framework for heavyweight dynamic binary instrumentation, Vargen is a lifesaver of a program for those who use unsafe language like C. Read this paper to learn about its very cool binary instrumentation technique. It's really quite impressive. To learn about its very cool binary instrumentation technique. Oh, okay, interesting. Quite impressive. Match a system software kernel. Although not the first project on microkernel per se, the Match, am I pronouncing this correctly? Most likely not. The Match project at CMU was well known and influential. It still lives today deep in the bowel of Mac OS X. Okay. Time sharing in large fast computers. One of the earliest reference on time sharing. Improving the reliability of commodity operating system. The first paper to show how microkernel-like thinking can improve operating system reliability. Alright. Okay, homework code. In this homework, we'll just learn about a few useful tools. Okay, in this homework, we will just learn about a few useful tools to examine virtual memory usage on Linux-based system. This will only be a brief hint at what is possible. You'll have to dive deeper on your own to truly become an expert, as always, right? Okay, the first Linux tool you should check out is the very simple tool free. First type man free and read its entire manual page. It's short, don't worry. Yeah, let's take a look at the main page here. Oh, shit. Wait, is this the first section of main page or the, what is it called? I'm assuming this is the first section of the main page, right? This one, not the standard library, I guess. Yeah, the command itself. Can see the command in user/bin free. Bin free /bin free. Okay, free display the total amount of free and use physical and swap memory in the system, as well as the buffer and cache used by the kernel. The information is gathered by parsing proc mem info. The display column are total, usable memory, mem total, and swap total in /proc/mem info. This includes the physical and swap memory minus a few reserved bits and kernel binary. Okay. Use or unavailable memory. Okay. Calculate as total negative available. Free unused memory. Mem free and swap free in /proc/mem info. Set memory use mostly by temfs sh mem in /proc/mem info. Buffers memory used by kernel buffer. Okay. Cache memory used by the page cache and slab. I'm still not sure about slab here, what this means at the moment. Buff/cache, sum of buffers and cache. So, oh, sum of buffer and cache. Okay. Available estimation of how much memory is available for starting new application without swapping. Unlike the data provided by the cache or free field, this field take into account page cache and also that not all reclaimable memory slab will be reclaimed due to times being in use. Mem available in /proc/mem info. Available on kernel 3.14. Emulated on kernel 2.6.27 plus. Otherwise the same as free. Emulated. Okay. Interesting. The same as free. This one. Okay, pipe. Okay. Debbie pipe. Is there any difference between kbbyte and kilobyte, or this one megabyte and megabyte. Is there any different? Right, there's flag for kilobyte and megabyte. Let me check difference between kbbyte and kilobyte. Okay. kbbyte.in oh, okay. Alright. Let me put this in the chat in case anyone wants to take a look. I know there was a disturbance in the force, but it was never enough of an issue to investigate. Anyway, basically there are two ways of using kill within computerizing of things, multiplying by 1000 as in 1000 byte, kilobyte, and using binary with an exponent of 10, like 210, which is 1024, not 1000. Okay, the binary, and depending on which you use, you'll get different size, and that's why we have often seen disappearing size in real life compared to advertisement. They were using the large number instead of the little one. The word is a strange space. The word is a strange space. Okay. Let me check the okay. I need to put the maxis. Let me put this in the chat too. Is anyone curious? Originally, kilobyte was loosely used to mean put 1000 and 1024 bytes, depending on the context. This caused a lot of confusion, right? Especially as storage devices become larger. To fix this, in 1998, the International Electrotechnical Commission (IEC) introduced new binary prefix KIB. It is 1024 byte, and MIB this byte, okay, and so on. This way, the binary and decimal system were clearly separated. Oh, okay. The binary representation is this one, but the decimal representation is kilobyte and so on. Okay. Well, let me read from the beginning, I guess. Have you ever wondered why your computer storage space seems smaller than what was advertised? Part of the answer lies in how data size unit like kbbyte and kilobyte are defined. Although they sound similar, they represent different amount of data, and knowing the difference can help you avoid confusion. Quick definition: kilobyte here, and then kbbyte. Notice the small difference. It may seem trivial, but at larger scale, the gap between 1000 and 1024 become very significant. Right here, read this basically because of confusion, right? The separation between binary representation and decimal representation, I guess. Real world example: hard drive. Let's say you buy a 500 gigabyte hard drive. Manufacturer's calculation in decimal, something like this. Computer's calculation, binary, using those P, the key maybe is that it? Yeah, maybe key, tapi, pepi. Yeah, at the moment, pepi is the largest, or petabyte, I guess, in the, what is it called? In the decimal representation. Okay, 1 GB equal this byte. Okay, 465 GB byte. Yeah, GB byte. Okay. Your operating system shows 465 GB byte instead of 500 gigabyte. No, you didn't lose space. The math is just different. Right. We are just using different representation, I guess. Common mistake: using kilobyte and gigabyte interchangeably. Right, even today, many apps, websites, and text pack incorrectly use kilobyte when they mean gigabyte. Situation RAM size. Okay, gigabyte make byte and gigabyte. Yeah, replace the last one with P. Like kilobyte turns into gigabyte. The binary representation. Okay. File download size, networking, kilobyte, megabyte, gigabyte, decimal base. If accuracy matter, like for developer, engineer, and nerd like us, you should always check which system is being used. Okay. Conclusion: understanding the difference between gigabyte and kilobyte isn't just academic. It impacts real-world storage, software, and hardware calculation. When in doubt, remember, gigabytes, 1024 bytes, binary word or representation, and kilobyte 1000 byte marketing word or decimal representation. And if your new hard drive looks smaller than expected, blame the prefix, not the seller. Okay. Multiple byte unit. The prefix kilo. Okay. The standard international use the decimal representation, I guess. But there's also the binary representation. Power of 2. Historically, the binary system used the identical prefix of the metric system but quantified differently. Alright. Let me wait a minute. Why is there a lot of let me check. Okay. I want to shorten the URL. There's a lot of query string there. Okay. Alright, now run free. Perhaps using some of the argument that might be useful. Test M to display memory total in megabyte. At least on Linux, test M is maybe byte, not megabyte. The megabyte is test mega here. The flag test mega here. How much memory is in your system? How much is free? Does this number match your intuition? Okay, let me check on another screen first. Okay. Alright. I think there is no problem. It is just printing out. What is it called? The total memory that I have is something like this. This is using maybe byte. This is using megabyte. Yeah, I have a swap space too. Okay, but currently didn't use any of it. So there is that. How much is free? Currently, I assume I have 9 gigabyte free. Around that size memory. Okay. How much is free? Yeah, I have around 16 gigabyte memory, something like that. Does this number match your intuition? Maybe. I mean, I'm not sure what kind of intuition that I should have. Next, create a little program that uses a certain amount of memory called memory.user.c. This program should take one command line argument, the number of megabyte of memory it will use. When run, it should allocate an array and constantly stream through the array, touching each entry. The program should do this indefinitely, or perhaps for a certain amount of time, also specified at the command line. Okay. I am still not sure. Okay, it should allocate an array. Right, I'm assuming we're gonna use malloc, to allocate the memory and constantly stream through the array, touching each entry. I'm not sure about this one. Constantly stream through the array, touching each entry. Touching its entry. Constantly stream through. I'm assuming we need to fill out the array. Maybe something like that. The program should do this indefinitely, or perhaps for a certain amount of time, also specified at the command line. Yeah, I'm assuming that create an array add array elements, I guess, something like this, or maybe fill up array element, maybe something like that. And for a certain amount of time, I'm assuming by how many megabyte of memory we will use, something like that maybe. Okay. Oh, alright. Okay, I think let's do this on the next session. So that's it for now. Thank you for watching and see you next time. Bye bye.